Hello, I just got finished recording my first run through the, what was it, fall 2019 final. So the most recent final if you're taking this class the same semester that I'm in. And it was frankly pretty brutal compared to a lot of these past exams. So this one should be no problem. Let's get going. Question 1, let's determine the interval where the solution is guaranteed to exist for this initial value problem. Dividing everything by t plus 2, we see that y prime plus 1 over t plus 2 times y is equal to 1 over t minus 1 times t plus 2. So this thing has some undefined behavior going on when t is equal to negative 2, when t is equal to, that's not a 1, when t is equal to 1, and nowhere else. So everywhere else on the number line, we're perfectly fine. But since our initial condition is for y at 0, so we're starting in between negative 2 and 1, we can only go, or we only have a solution that's guaranteed to exist between these two bounds here. So as far as we can go to the left without hitting discontinuity, and as far as we can go to the right. So that gives us a range between negative 2 and 1. The general solution of this thing right here is what? So this will be an integrating factor question. Y prime plus 2 over x times y is equal to e to the 3x over x squared. And remember, you have to divide out any coefficients that are on y prime to be able to use integrating factor, because now we can call this p of x and say that rho of x, which is our integrating factor, is e to the px. So that's 2 ln x, e to the integral of px dx. That's where I'm getting the 2 ln from. We can simplify this down to x squared and set up our solution. We know that y of x is equal to 1 over rho of x times the integral of rho of x times q of x, which is just our right side over here. So we will have x squared over x squared times e to the 3x. So we're really integrating e to the 3x dx. And so we get y of x is equal to 1 over x squared times 1/3 e to the 3x plus c. And that is c. If y of x is a solution to this differential equation here, then what is y at root 3? I believe this condition here says y at 0 is 4. So sometimes it's a little bit difficult to tell what you're supposed to do with this kind of question, especially when you're seeing a rational expression and you might want to try to apply the whole y over x equals v substitution. But, and this always happens to me, it's just separable. If you take a look, if we divide this side by y, we're left with our right side as a function of x and our left side as a function of y if we multiply our dx over. So 1 over y dy is equal to 4x over 2 plus x squared dx. And so taking the integral of both sides, we'll see that ln y is equal to, I believe this will be 2 ln 2 plus x squared, right? Yeah, that looks good to me, plus c. And so removing the ln from the left side, we can raise both sides to e. Well, no, take e raised to both sides. So e to the ln y is just y is equal to e to the 2 ln 2 plus x squared plus c. We can take this plus c and just bring it out as some constant c and rewrite this as c times x squared plus 2 squared. So because y at 0 is equal to 4, we can solve for our value of c. 4 is equal to c times 2 squared. So c is equal to 1. and we're solving for y at root 3. That's going to be 5 squared, 25. So 3 is B. 4, the general solution of this differential equation is what? Well, this is looking extremely exact to me. But since our exact equation needs to be in the form of the function m plus the function n dy dx, we'll need to take this negative and put it in there. So we're testing if nx is equal to my, those partial derivatives. And if that's true, then our equation is exact. Nx gives us 1, my gives us 1. So this is true, and we can integrate away and find our solution. We'll be taking the integral of m dx, which will give us, I can just do it, x cubed plus xy minus 4x, and we're comparing that with the integral of n dy, which is y squared plus xy. So we can set up our solution, making sure to only count our repeating terms twice and then all of our single terms once. X cubed minus 4x plus xy plus y squared is equal to some constant c. So looking around our answer choices, I knew I should have written that more clearly. This negative y squared right here, we lost that along the way because it looks like I wrote it like an underline. So this ends up being negative y squared. So our answer should be E for 4. Okay, we're on a roll. 5, determine the values of alpha, if any, for which all the solutions of this differential equation tend to 0 as t approaches infinity. So how I interpret this is that we can pull our characteristic equation out. That will be r squared minus 2 alpha plus 4r plus alpha squared plus 4 alpha plus 3 is equal to 0. And as long as both roots to this equation are less than 0, then the equation, the characteristic equation, which is just our solution y of t, will be equal to c1 e to the negative something times t plus c2 times e to the negative something else times t. And we know that when we have an equation in this form, the origin acts as an attractor, and all values will be, all starting initial conditions will be pulled in towards 0 as t approaches infinity. So in order to solve for that, all we need is a real part for our solution. And because we can have a conjugate imaginary part on there too, that will just contribute to some spiraling behavior as we go in. So we can set up negative b over 2, so 2 alpha plus 4 over 2, so alpha plus 2 plus or minus the square root of b squared minus 4ac. It shouldn't matter what's in there. That said, the solution that I'm getting here, you would think would just be alpha greater than less than negative 2. So are they just being rude and the answer is less than negative 3, 5D? Yeah, that's mean. Unless I'm missing something there, that's just a rude way to put it, because really, like negative 2.5 would make this real term negative. Maybe there's something that I am not catching though. So this method works, but it's a little sketchy, that's for sure. because it doesn't bring in any of the c terms. I'm not particularly sure. Question 6. Given that y1 is equal to t as a solution to this equation, which of the following is also a solution? If we divide everything by t cubed, so that the coefficient on y double prime is 1, we can apply the reduction of order equation, which states that y2 of t is equal to y1 of t times the integral of e to the negative integral of p of t dt, all divided by f1 of t squared dt. We can replace all of our y1s with t. That's what they tell us the first fundamental solution is. And then p of t is the term on y prime. So we get in here negative 1 over t squared dt. Double negatives will cancel. This integral gives us negative 1 over t. Now computing this integral is a little bit hard to see as u substitutions go, but if we set u equal to negative 1 over t, du is 1 over t squared, so we can say that this is t times the integral of e to the u du, or we just get y2 as t e to the 1 over, negative 1 over t. So e is our answer for 6. 7. The homogeneous differential equation given here has fundamental solutions given there. We're applying variation of parameters. So we know that there are really 4 terms that we need for variation of parameters. There's y1, which in our case is x, y2, which is x ln x. There's the Wronskian, which is the determinant of the matrix formed by x, our first fundamental solution, and its first derivative, and x ln x and its first derivative, which will be 1 plus x ln x. This determinant will give us x plus x squared. No, I wrote this wrong. There we go. 1 plus ln x. Product rule's hard. Not really. We get x plus x ln x minus x ln x. So our Wronskian is just x. Here we go. And the final term that we need is f of x, which is our right-hand side, as long as we've divided out all of the coefficients on y double prime. So dividing by x squared, we see that f of x is 1 over, not 1 over x squared, 1 over x. So then we know that yp of t is equal to negative y1, so negative x times the integral of y2 of t x ln x times f of x, which is 1 over x, times the Wronskian, which is x dx, plus y2 of t times the integral of y1 of t times 1 over x, our f of x, times x dx. We get 1 over x over here, so this integral will evaluate just to the natural log of x times the natural log of x squared. And then here we get ln x over x. We can do a u substitution where u is equal to ln x, and yeah, I'll write it out. U is equal to ln x, du is equal to 1 over x dx. So this integral will become the integral of u du. Taking that integral, replacing it, we get minus x ln x squared over 2, and then plus our x ln x squared. So overall we get x ln x squared over 2, 7 is C. 8. Let y prime denote a unique solution to this initial value problem. What is the value of y at 1? Okay, so solving this, we're just solving our characteristic equation, r cubed plus 3r squared plus 2r is equal to 0. R times r squared plus 3r plus 2 is equal to 0, which is r times r plus 2, r plus 1 is equal to 0. So we will get a characteristic solution, and since this is a homogeneous differential equation, that's our entire solution. Y of t is equal to, well, we have a root at 0, so c1 plus c2 e to the negative 2t plus c3 e to the negative t. Taking our first and second derivatives, y prime of t will be negative 2c2 e to the negative 2t minus c3 e to the negative t. Y double prime of t is 4c2 e to the negative 2t plus c3 e to the negative t. We can set up a matrix with our initial values and our y prime, and y double prime evaluated at 0. So 1c1 plus 1c2 plus 1c3 is equal to 2. 0, negative 2, negative 1 is equal to negative 1. And 0, 4, 1 is equal to 1. Moving this over a little bit, we can simplify everything down. Let's add 2 row 2's to row 3. That gives us a 0 here, a negative 1 here, and a negative 1 here. That turns into 1, 1. We can use that to set this to 0, 0, and this to 1, and this to 0, and this to 0, 1. Okay, so this tells us that C1 is equal to 1, C2 is equal to 0, and C3 is equal to 1. So if we are evaluating y at 1, we will get 1 plus e to the negative 1. So C is our answer for 8. 9. Let's find a particular solution to this second order differential equation. Okay, I'm going to take a nice little shortcut in here. Usually we would have to check our characteristic solution to make sure that we didn't have any overlap between what we were guessing for our y particular and the terms that are already in our characteristic solution. But since none, and if we found overlap, we'd have to multiply by t, whatever terms we're overlapping. But since none of our answer choices are multiplied by t, they're just sines and cosines, we are going to roll with that. So ypg of t, our guess for y particular, is a cosine t plus b cosine t. Ypgt prime is negative a sine t. Oh, I wrote cosine cosine, didn't I? This is sine. Plus b cosine t, and ypg double prime t is equal to, you know what, I did this last time. I did this during the most recent differential equations test that I took. We just have sine of t's and cosine of t's. I don't like writing so many of these for the the undetermined coefficient questions. So I'm just going to say c and s. This becomes an s and a c, and then we get ac plus bs. Nope. Nope, this is negative bs. There we go. See, maybe it's not the best idea. But we can plug these in. We will get ac minus bs plus 2as minus 2bc plus 5ac plus 5bs is equal to 20s. So all of our s terms together, we have negative b plus 2a plus 5b is equal to, that's a terrible 20, 20, and we can take all of our c terms together. That's a minus 2b plus 5a is equal to 0. So making a matrix out of this, 2a plus 4b is equal to 20. simplifying that a little bit. And then 4a minus 2b is equal to 0, so 2, negative 1. Adding two row 1s, subtracting two row 1s from row 2, we get 0, negative 5, negative 20, so we get 1, 4 here, and therefore 0, 2 there. So there's our 2 cosine plus 4 sine. 9 should be b. Okay, if y of s is the Laplace transform of y of t, the way I tried to read it didn't really work. If y of s is the Laplace transform of the solution to the initial value problem below, what is y at 0? Love this question. It just makes you take the Laplace transform, doesn't make you do the inverse. That's pretty great. But that said, we got to actually go solve the thing. So the Laplace transform of y double prime is equal to, I'm using alpha yet again. I hate writing s. It looks like too many of my other letters. My handwriting is not the best. It's alpha squared y alpha minus y at 0 times alpha minus y prime at 0. And then we don't need it here, but the Laplace transform of y is alpha y alpha minus y0, and the Laplace transform of y, we've already used it, but that's just y subscript alpha, the way that I'm writing things. So we can take the Laplace transform of both sides. All of these initial conditions will go to 0 because both of those are 0, so we get alpha squared y alpha plus 2y alpha. And what do we have over here? Well, we have u2 of t, and then some function of t where all of the t's are replaced with t minus 2's. And if I can grab, there we go. If I can grab our little sheet over here, we see that uc of t, where it's multiplied by some function of t, where all of our t's are replaced with t minus c's. That's just e to the negative cs, so e to the negative 2 alpha, and then the not the partial derivative, what am I talking about? The Laplace transform of f of t, so not f of t minus c. F of t is t e to the negative 3t. And we can scroll up a little bit and see that t to the first power times e to the negative third power will give us n factorial, so 1 factorial divided by alpha minus a, where a is that power, so we'll get plus 3 to the what power? The n plus 1 power, so squared. So we can factor out an alpha squared plus 2 and divide it, and we'll see that y of alpha is equal to e to the negative 2 alpha times 1 over alpha plus 3 squared times alpha squared plus 2. That's a bad looking alpha. Okay, and we're ready to solve because we are finding capital Y at 0. That's what I'm calling y alpha down here. So plugging in 0, we get 1 over 3 squared, so 9 times 2, 1 over 18. B is our answer for 10. 11, let's solve y double prime plus 4y is equal to 2 delta at t minus pi. And since these are our initial conditions, we are just going to use our formulas for the Laplace transform of y double prime and y. Yet again, we'll get alpha squared y alpha plus 4 y alpha, and that's equal to 2e to the negative pi alpha. That's using this formula, delta at t minus pi is equal to e to the negative pi alpha. Awesome. So taking this apart, we can see that y alpha is equal to 2, let's see, e to the negative pi, e to the negative, if I can write, pi alpha times 2 over alpha squared plus 4, just rewriting things a little bit. And that is That is looking good. We can just go over here and see that e to the negative cs times f of s, where in this case f of s is the Laplace transform of sine 2t. That's just going to be uc of t. So y of t is uc of t, where c is this guy, pi. So u pi of t times, well, what did we say the inverse Laplace transform of this thing was? That's just sine 2t, where we replace all of our t's with t minus pi. And there we go. Now, hold up, you might be saying, there's no sine of 2t minus 2 pi in any of these answer choices. The closest thing we have is option E, which is the correct answer, but for a really sneaky reason, and it threw me for a loop the first time I went through this exam. It's not actually that cool. And the sine of something plus 2 pi or minus 2 pi is the same thing. So we can take out that 2 pi, and it's just like going around the unit circle one full revolution. So yeah, 11z. I kind of hyped up that for nothing. Okay, let's find the Laplace transform of this function right here. We know that the integral from 0 to t of f at t minus tau times g of tau d tau is just the, its Laplace transform is the Laplace transform of f of t times the Laplace transform of g of t. So f of t minus tau, that will be this whole thing. So we can write f of t as e to the t cosine t. Then g of t is just everything that only has tau in it. That's t cubed. And we can take these Laplace transforms individually, multiply them together, and then we'll have our Laplace transform. So e to the t cosine t will be, let's see, the Laplace transform of f of t is what I'm computing right here. This will be alpha minus 1 over alpha minus 1 squared plus 1 squared, and then just going to circle our correct answer quickly. The Laplace transform of g of t will just be, the Laplace transform of t to the n is n factorial. 3 times 2 times 1 is 6, divided by s to the n plus 1, so n to the fourth. Sorry, alpha to the fourth. And that gives us, when we multiply those together by the whole convolution theorem thing that we've got going on right here, we get option C. Because if you expand this, you get alpha squared minus 2 alpha plus 2. So C 412. 13. This is a very difficult question to read. This isn't u of t. I'm pretty sure that's y of t. This is u1 of t. Let's find the value of y at 4. Okay, great. We don't actually need anything over here for this. We just need to know how the unit step function works. So let's use u1 of t as an example, and that's nowhere near big enough. There we go. It's still sloppy, but whatever. So between from 0 to 1, the unit step function u1 of t is equal to 0. At t is equal to 1, it's undefined down here, but defined at y is equal to 1, and then it continues along that path for all t greater than that. So all we have to do up here, if we're finding y at 4, well, we see we have a u5 of t. That hasn't activated yet, so that whole component will be multiplied by 0, and this will be this bit right here. This u1 of t will be equal to 1, so we can just ignore it, and this u3 of t will be equal to 1. So if we're evaluating this at 4, 4 minus 2 squared is 4 minus 3 cubed, which is 1, minus 2 is negative 1, plus 4 is, minus 4 minus negative 1 is 5. It's hard to say. Okay, let's solve this initial value problem here. y to the fourth power, sorry, careful, that's not y to the fourth power, that's y quadruple prime. And going by the scheme that they talk about down here, so you can just read off line 18 if you want the Laplace transform of the fourth derivative, or the nth derivative actually, of y, but we'll just do it here. Or I actually like using Roman numerals, I think that looks cool. But this Laplace transform will be alpha to the fourth y alpha minus alpha to the third y at 0 minus alpha squared y prime at 0 minus alpha y double prime at 0 minus y triple prime at 0. So you can kind of see how the power on alpha goes all the way down to 0, and the power, or the initial condition terms, go all the way up to the n minus 1th derivative. So we're taking the fourth derivative here, we end up with the third derivative's initial condition as our last term. So then easy by comparison is just y double prime, that's alpha squared, alpha squared y alpha minus alpha y at 0 minus y prime at 0. The sad thing is these first three initial conditions are all 0, so we can ignore this, ignore this, ignore this, ignore all these, and that'll just be a minus 1 on the end. So taking the Laplace transform of both sides, we will end up with alpha to the fourth y alpha minus 1. That minus 1's coming from that initial condition there, plus alpha squared y alpha is equal to e to the negative alpha. And that's just coming from the Laplace transform of delta at t minus c is e to the negative cs. Okay, looks good. Let's add that 1 over to this side and divide both of these by alpha to the fourth times alpha squared, which we can rewrite as alpha squared times alpha squared plus 1 over alpha squared times alpha squared plus 1. Okay, so if we can figure out the partial fraction decomposition of 1 over alpha squared times alpha squared plus 1, we'll be able to solve both of these, because the only difference between these two terms is that this one will have a u1 of t outside of it, and all of the t's in it will be replaced with t minus 1s. So I'm going to use the space over here to do our partial fractions. Alpha squared plus 1 is equal to a over, oh no, wait, it's got to be a alpha plus b over alpha squared plus c alpha plus d over alpha squared plus 1. I kind of really dislike these partial fractions. So multiplying both denominators up, so taking this whole thing, multiplying it into both of them, we will get a alpha cubed plus a alpha, nope, I want to order that differently, a alpha cubed plus b alpha squared plus a alpha plus b, okay, and then we get a c alpha cubed plus d alpha squared over there, and all of this is equal to 1, So I ordered it like this so that we can set up our matrix a little bit easier. 1a alpha cubed plus 0b alpha cubed plus 1c alpha cubed is equal to 0. We also know that but we have d to deal with too. 0d is equal to 0. There we go. Then for the alpha squareds, 0, 1b, 0c's, 1d is equal to 0. 1, 0, 0, 0, 0, and I'll need to expand this a little bit, 0, 1, 0, 0, 1. Okay, so subtracting here, and yeah, subtracting here, it's where we had a free variable there for a second. We see that both A and C are equal to 0, which is great news for us, that B is equal to 1, and that D is equal to -1. So both of these we can rewrite as e to the negative alpha times 1, let's see, B is equal to 1, so we get 1 over alpha squared minus 1 over alpha squared plus 1, and then plus 1 over alpha squared minus 1 over alpha squared plus 1. Okay, we can do the rest of this in our heads, or at least if you have a good enough idea of what's going on in this sheet, you can. So this inverse Laplace transformed will be 1 over alpha squared will just be t, and then we're subtracting sine t. So t minus sine t here, I like both of these. Now for our second bit, we said that this bit will just be the same with a u1 of t, and all of our t's replaced with t minus 1s. So D is looking good for 14. For 15, let's find the inverse Laplace transform of all of this stuff. So we're getting 3 terms in total for most of these answer choices. So it looks like we're going to have to do, partial fractions on the first bit, because this second bit we can do right off the bat. We can rewrite this as, let's see, 2 over alpha minus 1 squared. So that contributes the alpha squared and the minus 2 alpha, and a plus 1, so then we need plus 2 squared there. And that matches up very nicely with this whole formula for e to the at sine bt. So this will give us e to the t sine of 2t. Looks good. Okay. And how many of our answer choices agree with that? Well, these two, oh wait, yeah, these two do. These two don't. Those have 2 sine, 2 e to the t sine 2t. Okay, looks good. Let's do our partial fractions on this other bit. We have 10 e to the negative alpha. We'll leave that alone for right now. Let's just factor that out and remember to take all of our t's and subtract 1 from them. Speaking of which, we can get rid of, oh, look at that. We can get rid of both of these other answer choices, because we know that in the end, we're going to have u1 of t. We're going by this rule, by the way. Because we have e to the negative cs times some f of t's Laplace transform, we will get u1 of t times that function whose Laplace transform you need to take to get that capital F of s, where we replace all of our t's with t minus c. So A has to be correct, but let's make sure, because, okay, yeah, there's no because. So we're partial fractioning 1 over alpha squared minus 5 alpha plus 6. This is equal to 1 over alpha minus 2 alpha minus 3. Yeah, okay, that works. And this is equal to A over alpha minus 2 plus B over alpha minus 3. At least this one will be easy. So A alpha minus 3 and B alpha minus 2B, and this is minus 3A. All of this is equal to 1. So we can make a matrix A alpha squared plus B alpha is equal to 0, and negative 3A minus 2B is equal to 1. There we go. Adding 3 row 1s to row 2, we get a 0 here, a 1 here, and then we can subtract and get our negative 1. So this will give us our negative 1 over alpha minus 2 term will give us this negative e to the 2t, and then we replace our t with t minus 1, and then the positive 1 over alpha minus 3 will give us the e to the 3t minus 1. So 15 is A. Okay, given x prime equals ax, which of the following are values alpha such that the origin is a saddle point in the phase plane? Let's solve for the determinant of a minus lambda I. That will be 1 minus lambda times 1 minus lambda minus 3 alpha is equal to 0. Alpha squared minus 2 alpha plus 1 minus 3 alpha. Did I call that alpha? That's lambda. I'm getting mixed up. That's equal to 0. Running this through our quadratic formula, we will get negative b over 2, so 1 plus or minus the square root of b squared, which is 4 minus 4ac, so minus 4 plus 12 alpha all over 2. This gives us 12 alpha in here. We can square this 2 on the bottom and move it into this square root. Dividing by 4, we get 3 alpha. And so I should have talked a little bit more about what we're actually looking for here. So the origin is a saddle point in the phase plane if and only if our eigenvalues are completely real and have opposite values. So in order for us to get a positive and a negative eigenvalue out of this, the magnitude of the square root of 3 alpha has to be greater than 1, so that when we subtract it from 1, we go past 0 into the negatives. And that's only true if 3 alpha is greater than 3, so alpha has to be, no, not greater than 3. That's not what I meant. Greater than 1. Yeah, so alpha has to be greater than 1/3. 16 is A. 17, let's find the general solution to this system. Finding our eigenvalues, 2 minus lambda, negative 4 minus lambda, minus 7 is equal to 0. Lambda squared plus 2 lambda minus 8 minus 7 is negative 15 is equal to 0. Lambda plus 5, lambda minus 3 is equal to 0. Lambda is equal to 3 and negative 5. So we can get rid of all these 2 and 4s that they have going on there. 4 lambda is equal to 3. A minus lambda I will be negative 1, 7, 1, negative 7. We can simplify this to 1, negative 7, 0, 0, and make an eigenvalue of 7, 1 out of that. I'll have to go up here, for lambda 2 is equal to negative 5, we will get 7, 7, 1, 1. We can simplify this down to 1, 1, 0, 0, and find an eigenvalue of negative 1, 1. As a result, I'm running out of space. I'm writing too big. Oh, we don't need these anymore. That's some space. As a result, we can write our x of t as c1, lambda 1, not lambda 1, v1, so 7, 1, e to the lambda 1 t, which was 3t plus c2, negative 1, 1, e to the negative 5t, and that is option D for 17. Which of the following is a solution to this non-homogeneous system right here? So the guess that we're going to be making is a e to the negative 2t and b e to the negative 2t. And we would have to check to make sure that negative 2 isn't an eigenvalue for our homogeneous system here. But, well, we can do it right now. If negative 2 is an eigenvalue, then the determinant of 3, 1, 4, 0 should be 0, which it is not. So it's not an eigenvalue. That is great. It's great for us, because it means that this can just be our guess here. So we need to assign this as x, and then our x prime will be negative 2a e to the negative 2t, negative 2b e to the negative 2t. And before I plug anything in, let's notice that if we plug x and x prime in, every single term throughout the entire equation will be multiplied by e to the negative 2t. So I'll divide that out from everything and just act like it's not there. So we have negative 2a negative 2b is equal to 1, 4, 1, negative 2 multiplied by ab. So we can say that negative 2a is equal to a plus b. Oh, whoops! I forgot to I forgot to add our 4 plus 4, 0. There we go. So a plus yeesh. Okay, negative 2a is equal to a plus b plus 4, and then down here negative 2b is equal to 4a minus 2b, and that's it. So let's set up a matrix here. If we move this over as negative 4 and add this over, so we have 3a. 3a plus 1b is equal to negative 4, and 4a plus 0b is equal to 0. As a result, we can use that second row to set that 3 to 0. And so b is equal to negative 4, b is equal to negative 4, a is equal to 0. And as a result, we get c as our answer. We can now pretend, we'll stop pretending that e to the negative 2t doesn't exist. So 18 is c. 19, given that x is equal to e to the negative t times beta and then 2 is a solution to this, find beta. Let's just plug this thing in. Let's plug its first derivative into our left side. We have, okay, here, I'm going to do it again. We have an e to the negative 2t in every single term. So x prime is e to the negative t times negative beta negative 2. So I'm just going to plug in negative beta and negative 2, and that for x prime, and then beta and 2 for x. Negative beta negative 2 is equal to negative 3 negative 2 5 4 times beta 2. We can expand this out. Negative beta is equal to negative 3 beta plus 10, and negative 2 is equal to negative 2 beta plus 8. Since we only have one variable to work with and two equations, both of these have to be identical. So we can subtract an 8 over here. Negative 10 is equal to negative 2 beta, or beta is equal to, that's a b, but whatever, you know what I mean. Beta is equal to 5, so 19 is b. And our final question, the general solution of this thing, can be written as what? We're going to get some complex eigenvalues here, so let's get those. If we solve a minus lambda I, I do that every single time. The determinant of a minus lambda I equals 0. We're solving negative 1 minus lambda times negative 3 minus lambda plus 10 is equal to 0. Lambda squared plus 4 lambda plus 14. Is that correct? Just making sure. I think so. 14 is equal to 0. Negative b over 2 is negative 2 plus or minus the square root of b squared. 16 minus 4 times 14. 14 times 4. Oh, that's what I did. Okay, I remember. No. Okay. When you multiply 1 and 3 and then you add 10 to it, it's actually 13. Fun fact. And I remember this now, because 16 minus 13 times 4, I had to do it manually. Not manually, but I had to look it up because I was too lazy before, and I have a calculator sitting right next to me. So that's minus 52, I'm pretty sure. Whatever, it ends up being negative 36 over 2, so this is 6i, blah, 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 3i, like that. So we can plug in one of these eigenvalues. Let's say that lambda is equal to negative 2 plus 3i to a minus, I need more space, a minus lambda I. So we will have 1 minus 3i, negative 2, and then 5, and negative 1 plus 3i. So we can take this first line. This says 1 minus 3i times x1 is equal to 2x2, and make an eigenvalue out of it. An eigenvector. That will be 2 and 1 minus 3i, like so. Okay, and now all we're doing is taking this eigenvector 2, 1 minus 3i, multiplying it by e to the lambda t, which is e to the negative 2t, and then we can split off into another e to the 3it. This 3it, well, exponentiated will become cosine, I don't need that second one, cosine 3t plus I sine 3t, and we can expand this into a real portion of our solution and an imaginary portion of our solution, and we'll be good. So we'll have c1 e to the negative 2t, we still need those, and then the real portion of this solution. We'll get real values when we multiply cosine on the top to that 2, so 2 cosine 2t, and when we multiply, yeah, that's the only one for the top, and then when we multiply cosine by 1, so cosine 3t, and I sine 3t by negative 3i, that gives us plus 3 sine 3t. So now we'll add c2 e to the negative 2t times the imaginary bits that we get. We'll get negative 2i up top, so 2 sine 2t. I'm not sure why I said negative. It's just 2i sine 2t, drop the I, we get 2 sine 2t. And then on the bottom, if we multiply cosine by that cosine by that negative 3i, we'll get negative 3 cosine 3t. I'm not sure why this is a 2, that should be a 3. And then if we multiply I sine 3t by 1, we will get plus sine 3t. Now let's see how they're writing these up here. I'm not sure whether it got cut out, but I either said or didn't say, I definitely have said in every single other recording I've made of this question, that I'm not sure why their answer is what their answer is. And it's actually because every single time I've recorded it, I've used this bottom row here to make the eigenvector, which is perfectly legitimate, and I got an answer that's identical to their answer, but it doesn't look like it. It's very different. It has 5s running around. None of our answer choices up here have 5s. That's mainly what was throwing me off in the past. But this should be one of our answer choices. So we have our cosine 3t times 2, 1. That's the vector made out of those two components. And then we should have 0, 3. So that brings us to these two. Then cosine, let's see, we should, did I screw something up here? Oh, wait, have they switched these? Cosine 2, 1, nope, sine plus 2, 1, minus 3? Yeesh. It looks like the signs of our cosines are off. Okay, I figured out what they did. It's actually extremely, extremely rude. Just saying. So C is our correct answer. If this constant is multiple, if we factor a negative 1 out of everything that we have over here, we will end up with 0, positive 3 for cosine, and negative 2, 1 for sine. So yeah, they're right, but that's still a little mean. Also, I don't really like this question in general because of this design where if you use that second line to find your eigenvector, it ends up not giving you the same thing. Maybe that's just a me thing. But either way, we are done, and this will definitely edit to under an hour, so that's nice.